Well, when Mark asked me to do this, I was all set to come up with a real technical science lecture, but then he said, well, it's got to have some non-science interest to it. So I scratched my head and came up with a title, Aerosols, Climate, and Poetry. Well, aerosols and climate's easy. That's what I focused on for pretty much my whole career. It's the poetry part that something about me that you probably never knew and certainly never appreciated and probably still won't appreciate it, is I'm an international prize-winning poet. Hold your applause. So I went to Siberia in November, a couple of years ago, for a workshop on Siberian aerosols. You got to question the sanity of somebody who voluntarily goes to Siberia in November, but okay, we can continue doing that. So, you know, as in any conference, and especially in Russia, there's a lot of toasts going on. And after a few of those, they said, well, we're going to have a contest, and everybody has to write a poem. And they handed out pieces of paper with what the general subject of your poem was supposed to be. And mine was to write about the people of Tomsk, Russia, which was where the conference was, which was a bit of a challenge. But I'd gone out at lunchtime to eat lunch, and I watched the people feeding their squirrels. And so I wrote a poem about how nice the people of Tomsk were because they took care of their squirrels. Now, you probably want to hear my poem, don't you? Well, that lower right picture kind of explains why I've managed to forget my poem. There was a fair amount of Russian vodka involved in the process. But I did bring my prize. I can pass it around if you want to see it, but it's a Christmas tree ornament. So, aerosols and climate. Oh, I'll come back to Siberia, by the way, because there was a reason I went there. What's climate? It's the average of weather over a long period of time. So these people who want to criticize climate change by saying, well, you know, it's snowing in Washington, D.C., therefore it can't be global warming. You know, it can be cold someplace, but when we talk about climate, and especially global climate, we're averaging over time, over many years, and over the entire globe. So even though you have an unusually warm summer in Europe, well, somewhere else it may be unusually cold. And it's those averages that people can't do themselves really very well. So what are aerosols? Tiny particles suspended in air. And there are all sorts of different kinds of particles. They come in different sizes, different shapes, different chemical composition. And their climate effects depend very much on those properties of the aerosols. The soot particle, for example, is a very special part of it, of the climate puzzle, because that's the strongest absorber of solar radiation in the condensed phase in the atmosphere. So what are the effects? Well, I'm really only going to talk about one category of effects, and that is the direct interaction of particles with solar radiation, because they scatter light, so they redirect some of that incoming radiation into different directions, and they absorb light. So the picture and the numbers there are the grand averages for the northern hemispheric Indian Ocean for a 3-month period in 1999, and we went down there and we both sat on an island and this is in the Maldives, sat on an island and made measurements for a few months, but also the National Science Foundation's C-130 research aircraft went down and we had instruments on that. And these numbers are the average perturbation to the Earth's radiation balance that were attributable to aerosols due to the scattering and absorption. 7 watts per square meter at the top of the atmosphere. So that's essentially the loss of energy to the Earth system. 7. That doesn't sound like a very big number, does it? Where's my straight man? Roses. What's the incoming? Yeah, they're about 1,000. We'll round it off. But that's with the sun directly overhead, midday. This is the average over 24 hours for several months. That cooling at the surface is those 23 watts per square meter. That's actually like about a quarter of the amount of energy that the ocean is absorbing. So these are big numbers for that particular region. So the effects, we warm the atmosphere because particles like soot are absorbing solar energy. They heat the atmosphere, which also means there's less energy reaching the surface. And that top of the atmosphere effect then is the difference between those two. So this direct forcing, that's just one part of the puzzle. There are other aspects of the puzzle, and I'll briefly touch on them later. The biggest one is interactions with clouds, because every single cloud droplet, every single ice crystal in the atmosphere has formed on an aerosol particle. So when you change the properties of the aerosols, you change the properties of the clouds. We've been at this for a long time, and this figure is from Scientific American about 25 years ago. And it's a model calculation of the global distribution of the perturbation of the energy balance. So if you can see the numbers at the bottom, these really dark parts of the map are -1 watt per square meter, 0 watts per square meter, all the way up to 3 in the yellow regions. And this calculation is done for two components, sulfate aerosols and carbon dioxide warming. What you see is a very patchy picture. From the aerosol side of that, that's because particles don't reside in the atmosphere very long, so the atmosphere is not well mixed. And that's why you see so much cooling, the bluish and darker blue colors, in a few specific regions where there are a lot of sulfur, industrial sulfur emissions. Well, that's another part of the problem of understanding how aerosols are affecting climate. Remember, there's a whole bunch of different kinds of aerosols, and we see very non-uniform distributions. That means that in order to understand the climate effect, we need to be making measurements in a lot of different places. It's very different from the greenhouse gases. Turns out if you measure carbon dioxide up on the Mauna Loa volcano in Hawaii, which is where NOAA and Scripps Institute of Oceanography have been making measurements for 50-some years, that actual one-point measurement can give you a pretty good handle on the global average. Can't do that with aerosols. So what I spent a lot of my career doing was putting dots on the map. Very few of those dots are sites where we're actually making the measurements ourselves, going to the site, calibrating instruments, fixing problems, doing all the data analysis ourselves. Most of those stars, though, are from other places, other institutions that are making measurements, and our goal was first to recruit people to join in this effort, and then to make sure everybody's on the same page in terms of making measurements the same way. This brings me back to Siberia, because you'll notice there are a lot of really big empty spaces on this map. And Siberia is one of them. And the reason why we went to Siberia was to get that dot on the map. Well, what do we do with these measurements? Well, one of the things that is done is use them to test models of climate forcing by aerosols. Remember, forcing is the word I'm using to describe a perturbation of the radiation balance. The blue line is what you get with a model without aerosols in it, just greenhouse gases. The black line's the observations, and all the band of yellow is a whole range of different model runs. But what you see is that blue line is very different from the observations. And it's not until you start putting in observations of aerosols into the model that you get much better agreement between what's observed and what the model's predicting. And it's these kind of results that lead to the ever-increasing confidence that come from the international assessments of aerosol effects on climate. How many have heard of the Intergovernmental Panel on Climate Change, IPCC? A few. It's the international organization that's coordinating assessments of climate effects, human effects on climate. And their assessments really represent a consensus of a large number of scientists from all around the world. That consensus also involves governments in terms of approving the final wording. And I've never been to one of those meetings, but I understand that the discussions get pretty intense about specific words that get used, especially from countries who are so dependent on combustion of fossil fuels for their economies. I did get to take part in one of those IPCC assessments as one of the official US government reviewers. So this report, big, huge report, is generated and sent out for comments. And anybody can comment on it, but then there was a panel of government scientists who had to prepare the US government assessment. So this slide, what can you see that from back there? Going down from the top, what is being shown is the radiative forcing. Here's the zero line. Going to the left is a cooling. Here's -1 watt per square meter. These are top of the atmosphere global averages. And the warming. So carbon dioxide up at the top, it's got the biggest single bar, and a fairly modest uncertainty range here. Carbon dioxide's number is a bit over 1.5 watts per square meter. So that's what much of the fuss about carbon dioxide is about, that 1.5 watt per square meter perturbation of the energy balance. So the assessment goes through a whole range of different gases that absorb infrared radiation, because that's where the effect of the gases is absorption of outgoing terrestrial radiation. The aerosols are down here in the bottom, and the different colors represent different types of aerosols. Remember that picture I showed you of what electron microscope photographs of aerosols look like? They're very different. Well, this is breaking them down into their effects. Most of them are cooling, but black carbon, the soot, is a warming effect. So you've got to put all of those pieces together to get the overall effect of the aerosols. And then there's the effect on clouds that I mentioned briefly, with the biggest uncertainty bar of all. And these letters over here, the level of confidence in those assessments, the lowest confidence of all. Another effect is absorbing particles falling in snow, which leads to a change in the reflectivity of snow, which means it'll melt faster. So this is putting together those different numbers with their uncertainties to get a probability distribution of the radiative forcing, watts per square meter, greenhouse gases here, centered on about 3 or a bit over 3 watts per square meter plus, aerosols down around -1 watt per square meter, and then the total human-caused climate forcing with a pretty wide uncertainty range. What are the consequences of that uncertainty range, and why are then we putting so much effort into making those measurements? It comes back to the concept of climate sensitivity. So I had to put one equation in my talk. Climate sensitivity is the temperature change, the change in global mean surface temperature associated with a given radiative forcing, a given perturbation in the radiation budget. It's normally expressed as degrees centigrade associated with a doubling of carbon dioxide since pre-industrial times. Don't worry too much about the different color bands because those are all associated with different scenarios, emission scenarios that were considered in the IPCC report. But I want you to look at the range of these values. So what's being plotted is the equilibrium temperature change, and equilibrium is something in the climate system that takes a long time, versus the concentration of greenhouse gases as an equivalent concentration of carbon dioxide. The two curves, the lower bound curve, the upper bound curve, show the range of climate sensitivity that is considered to be most likely in the IPCC assessments. And it's a pretty wide range from about 2 degrees to 4.5 degrees. And it's interesting, that range has not, over several decades of research, that range has not decreased very much, in spite of a huge amount of effort being put into it. And what that reflects is not a failing of the researchers trying to quantify that, but it means it reflects that they've learned more and more about what they didn't know. What's the phrase? The unknown unknowns? Is that what we use? That's what's associated with the fact that that uncertainty range hasn't changed a lot. But there's a lot of talk about, well, let's try and stabilize the temperature change to 1.5 degrees or maybe 2 degrees centigrade. If you look at this horizontal line, a 2-degree increase since pre-industrial times as a function of the greenhouse gas level, if the sensitivity is at the high end of that range, that stabilization concentration is down around 380 parts per million. How many of you know what the current concentration of carbon dioxide in the atmosphere is? Yeah, you're back when we were at Harvey Mudd. It's a bit over 400 now, and continuing to rise. Well, so we're already committed to that 2 degree if the climate sensitivity is up there on the high end of the range. Forget about 1.5 degrees that they talk about. That's even less probable. If the climate sensitivity is on the low end of the range, we're down around 550 for that stabilization. So what that means is, all right, if we want to hold it to 2 degrees, we've still got a few years before we've got to quit emitting CO2. But the end result is, one way or another, if we want to avoid major warming of the climate, we've got to quit burning carbonaceous fuels. So how do you get that sensitivity? That's such a key number. It's not something that gets programmed into a computer model. Rather, it's an emergent property of the model, where it's the sum effect of all the processes, all the feedbacks in the model lead to these numbers in the range of 2 to 4.5 degrees. That's one way to get at it. Another way to get at it is to pick an event or a time period where you think you understand the forcing and you think you understand the temperature response to that forcing. Take a volcano, for example. That's a major perturbation in the climate system. And I actually skipped past that on my slide showing the model results earlier, because if you notice the big dips at certain times in that, those were volcanic eruptions. But if you know the forcing and the temperature change associated with it, you can estimate the sensitivity. Well, the point is, if you're going to know the forcing, you've got to be measuring the aerosols, and you've got to do a really good job of it. So I promised you poetry, and I have a real poem for you now that I want to conclude with. Frogs in a pot. Are we deluding ourselves that we're not? I remembered this poem. Well, I told my sister about this poem. Well, I told her the Siberia story first, and then I told her the story, or I told her this poem, and her comment was fairly pithy, and it was, there was a little bit more Russian vodka that was needed in my poetry endeavors. So with that, thank you very much.